Okay, so hi everyone. I'm Tom Hodgson and I'm going to talk today about coding principles. Now, before I start, I was going to have a really trendy branded Northeast themed backdrop, but I really like the insight into our colleagues' lives that lockdown's given us. So I'm going to keep it completely like this, and you get to see Beauty and the Beast. I can't promise my 3-year-old will walk in wearing only his pants like he did in the first call of lockdown, but you never know your luck. So let's get started with coding principles. Programming languages are designed to be as flexible and as powerful as possible. And this means that there are an infinite number of programs we can write to perform an infinite number of tasks. But an interesting consequence of this is that there are an infinite number of programs we can write that all perform the same task. So if you come to me and ask me to write some software to fix a problem, and there are an infinite number of ways I can do that, and there are an infinite number of programs that are all different that solve the same problem. And this talk is all about how we answer the question, which one of those programs is the right program? What's the right way to write our code? So we're going to draw up what we'd like to do is draw up a list of guidelines about how to write our code, and that's not an easy thing to do, and more companies do it poorly than companies do it well, and the industry trends over the last 5 years, the way we actually build and deploy our software has actually made it even harder. And I'm going to illustrate that with a case study. And the case study is sales cycle. So sales cycle is a lot like Google Analytics in that a client will install a script on their website. And this script will start sending information to sales cycle servers about what the users are doing on the site. One of the things that sets sales cycle apart from Google Analytics is the messages are bi-directional, so we can actually send messages back and show them directly to the user, and that allows us to influence their customer journey. Now, the problem with all websites is that as the number of users increase, the load on their servers increases, and it slows them right down, and eventually they grind to a halt and your website stops. Now, if you are a company like SalesCycle who has hundreds and hundreds of clients, then you have to manage the traffic of hundreds and hundreds of websites. And so the problem is hundreds and hundreds of times worse. Now, the solution is quite simple. You just have more servers than you need, so you can spread the load across those servers. But there's a problem, and the problem is that the traffic isn't constant. So the load on those servers tonight at 9 o'clock is going to be a lot higher than it was this morning at 5 a.m. And there are cycles on longer timescales as well. So the peak load on a Saturday night is much greater than the peak load on a Tuesday night. And even across a year, right now in November, as we get closer and closer to Black Friday, and again on Boxing Day, the load on those websites is much, much greater than the rest of the year. So you can, or at least it's not a good solution, to spin up enough servers to handle your peak load, because for the vast majority of the year, they're going to be sitting around doing nothing. Now, this isn't just a problem for SalesCycle, it's a problem for anyone who uses web traffic, and the solution's well known. We rent servers from a cloud service provider. SalesCycle use AWS, but there's also Google Cloud, Azure, and countless others. And we write our programs so that they're easy to start and easy to stop. And so at SalesCycle, we have a little mantra called serverless first. And what this means for us in AWS is that we use a lot of AWS Lambda. And what this means is we just write the code and we put it somewhere, and that's all we do. We don't know anything about the hardware that it's running on. AWS tells us how many times it's been run, and they charge us accordingly, but we don't know if it's run across 20 servers or they've all been run on the same server. And AWS manages our application for us. So at sort of 6 o'clock in the evening, when people start coming home from work and they start internet shopping, AWS starts spinning up instances of our application so it can deal with that load. And then again at 10 o'clock, when people start going to bed and stop shopping, AWS starts killing our application and stopping them. And this has led to a pattern of microservices. And so we start writing small self-contained repos, small contained applications that just do a single thing. And this gives us fine control on the services that we can spin up and spin down. But it also leads to the biggest mantra of all at Sales Cycle, which is use the right tools for each job. So traditionally, when you have this big monolith application with all the code of your company in it, it's one program that does everything your company does. You need to choose a tool, a tech stack, and a language that can do everything it needs to do. So you end up with quite a generic solution. You know, it's a jack of all trades solution. It's okay at everything. But once you swap over into this paradigm of microservices, of small applications that just do a little thing, we have lots of these, but each one just does a little thing, you can use the best tools for that specific job. And it doesn't matter if the tools you use are rubbish at everything else, as long as they do that one thing well, then you're in business. And so let's have a look at some examples that we have at Sales Cycle. So the front door into the Sales Cycle application, there's lots of websites all over the world sending data to them. And there's a lot of data. It's coming in quickly and it's all in JSON form because it's coming from the web. And so we need something that's good at dealing with JSON. And Node.js is good at dealing with JSON. But as developers, we want some kind of type safety. So we find our errors as soon as possible at compile time. And so the front door services are written in Node.js, written in TypeScript, hosted in Node.js, usually in an ECS in a Docker task, but sometimes Lambda. And that's the right tool for that job. As that data then goes into the system a bit further, we need to make decisions based on that data. So we need to decide whether to show a message to that user or not. And we have to look at all the past data that's happened. So for example, have they looked at this product in the last week? Have they looked at a different product in the last week? And then we need to make this decision whether to show the message, and we need to do it fast because it's got to happen on the click of a button. So the user's clicking a message and it needs to be there immediately. And so for this, we use an in-memory computing grid and we use Ignite. And Ignite's a JVM tech, and the code, the clients that we write that query that data grid are going to actually join the cluster. So it makes sense for them to be written in the JVM tech as well. I like Java, but a bit verbose for me, so I prefer Kotlin. So we chose to write these services in Kotlin, and they run in a Docker image, and we also have some that run in a Lambda. Then for every user, for every client all around the world, we need to maintain a WebSocket connection to actually push the messages down to that user. Now there's a lot of them, so we want as little memory overhead as possible because we're going to have to manage a lot of these sort of these connections. And we wanted something that dealt well with WebSockets as close to natively as possible, so in the standard library. And that's why we chose Golang, and we have some Golang services written in, hosted in ECS again. And so there are three examples of very different technologies hosted in different environments and written in different languages and actually different programming paradigms. And the question is, how do we share and collaborate across these teams? How does the team working on functional TypeScript hosted in a Lambda communicate the way they program and compare the way they program with the team writing object-oriented Golang hosted in an ECS image? Okay, so I'm going to give you a list of coding standards, and from this day forward, you should never commit another line of code that does not adhere to each and every one of these standards. Every time a pull request comes in, you're going to have to get a nominated approver, and they're going to have to write down every single rule and then individually sign each one of them off with evidence that they conform to the rules. If they don't conform to the rules, then you're going to have to revert it and start again. It's absolutely imperative that we don't let a single line of code that doesn't adhere to these standards into the main branch of the code base. Okay, I mean, obviously we don't want it to be like this, and I've seen pretty similar things in places in the past. But what's really important is that coding standards shouldn't slow you down, they shouldn't be a chore, and they shouldn't be applied retrospectively at the end of a piece of work. And you should think of coding standards as just the same as personal development. It's just something we're going to get better at as we progress as software developers. And it's certainly not a gate that it's got to get through to be good or bad. The other thing I want to stress is that I'm going to show you some of my coding principles, some of my coding standards. But that isn't what this talk is about. This talk isn't about me delivering a list of standards for you. They might not be the right standards for you. This talk is about introducing a language and a visualization that allows us to discuss coding standards and understand the consequences of the decisions that we make. Another thing to mention, I'm not interested in formatting. It just bores me. I don't care where your brackets or your new lines or your commas are. I think it's important to have consistent formatting. I think it's important for two reasons. The first reason is that it anonymizes your code. So as a tech company, we want to deliver a single thing. We don't want to deliver bits and pieces where you look at one bit and go, I know who did this, I tell what they did with the commas, and oh yeah, I know this belongs to this developer. We as a tech company, we want to produce a thing that lives beyond the developers. And the second reason it's important is because it's just noise. When a pull request comes in, if something's a bit different, if something you haven't seen before, then it distracts your attention, and it distracts it away from the things that are important that you should be reviewing, the business logic. So consistent format is good. Get a linter, stick with it. It doesn't really matter which one, but I'm not going to mention that for the rest of the talk. And every coding standard should make the development team more productive. If it's not making you more productive, get rid of it. And this is a long-term thing. It's no good being productive for a week if you then have to spend 6 months tidying up the mess. Okay, so this is my first coding principle. As much code as possible should be tested without network connectivity. Now, I went back and forth a bit on the wording here, but the point is that any programming language that we write that does something useful must interact with the outside world, and it must interact in the outside world in a way that interacts with humans. So, for example, it might send me a text message when my tax is here, or it might post a picture online for my friends to see. But the problem is if I'm going to test the code that does that, I need to set up some infrastructure. So I might have to set up a phone to send a message to, or a website to send the pictures to. And that prevents me just pulling the code from GitHub and running the tests. Prevents me running the tests on the train as I go through a tunnel. So I would like as much code as possible to be tested without interacting with the outside world. And the way it usually interacts with the outside world is through the network, and that's why I've worded it like that. Now I'm going to show you some coding samples. Please don't read them line by line. At this point, it's just the big picture we need. This is some functional TypeScript, a few TypeScript functions. And in the middle there's a line that says await query, and there's some SQL. So that's hitting a database. That's talking to the outside world through the network to a database. Here I have some object-oriented Java, and in the middle of the code somewhere, there's a line of code that's talking to an API endpoint to get a weather report. And so that's going through the outside world on the network. And finally, just to prove a point, here's some Fortran. No objects, no functions. And, well, that's not true, but it's Fortran. I have no idea what it's doing because it's Fortran. But there's a line there saying SQL execute and SQL fetch. So I'm guessing that that's going out to a database. But the point is, it doesn't matter what the program language, what the paradigm, what the stack stack. There's going to be some lines that hit the network, hit the outside world. But all I want is as much code as possible to be testable. So some's going to have to, but some isn't. And I would expect every other line in all three of those programs to be testable. So we have to come up with a way of designing our code, of structuring our code, so that we can test pretty much everything, but just ignore a few lines here and there. And to do that, we need to come up with the concept of a unit. Now, a unit is any code that you can run independently. It might have some, so it's any code you can run independently, and here's a visualization of it with this big green square. It's going to have some inputs. So let's, for example, imagine a unit of code that tells me if the length of a string is greater than 10 characters long. It's going to need the input of a string to check, and it's going to output a boolean yes or no, it's greater than 10 characters, or it's not greater than 10 characters. And so the inputs come in at the top left, and the outputs go out at the bottom left. It's probably going to perform some computation. So in that case, the unit will need to check the length of the string and compare it with the number 10. and it might affect the outside world. It might interact with the outside world. It's what we call cause a side effect. And you can see here there's a little gap in the unit with an arrow leaking out to affect the outside world. And this is the bit that needs the network connectivity usually, and this is the bit that is the useful bit. The code interacts with humans, interacts with the outside world. Units are synonymous with classes, but they're more than that. Units are just some code they can run. They can equally be a function, equally be a file. If you just have a file of JavaScript line after line, imperative code, then it's just a file. And it can even be a directory of files. You might have loads of code spread out across different directories of files. If there's just one function you can run at the entry point, then you've just got a single unit. So think of that big green square as just some code that you can run. It has inputs, it has outputs, and it might affect the outside world. Units can depend on other units. So again, let's go to our example of a string. Then we're checking whether its inputs, whether its lengths are greater than 10 characters. And it may be that we just have a single unit. The input comes in, we run a computation, input.length greater than 10, and we return the result as the output. But it may be that that unit delegates some of its work to dependency units. So here it's got two dependencies. The first dependency A, all that can do is calculate the length of the string. A dependency B, all that can do is compare a number with the number 10. But the main unit now composes those units together to perform the logic of first getting the length of the string and then comparing it with the number 10. So I'm going to go a bit deeper into this example and show you some code. And this is a Java-based, class-based representation of those units. So I have a class definition for dependency A and a class definition for dependency B. Dependency A has a single function that takes the string and returns a number. That's going to tell me how long that string is. Dependency B has a function that takes a number and returns a boolean that compares the number with the number 10. Is it greater or less than 10? And then I have a class definition for the unit itself. And the unit is constructed with its dependencies, and that just has a single function that I can run as well, called execute. And all it does is it takes its input, passes it to its first dependency, it takes the output from the first dependency and passes it to the second dependency. And then it takes the result from that dependency and uses that as its output. And this is called function composition. It's just composing the two dependencies together. And the bottom two lines show you how you create an instance of the unit with its dependencies and how you create its dependencies. And then the very bottom line shows you how you run the unit and get a result back. Now, if we have a look at the constructor, it's something that takes two dependencies and returns a unit. Now, if I draw this as a picture like this, those of you who've done functional programming it will shout out at you, it's a function, it takes two things and gives you something back. And so we can draw up an exact analogous system using functional programming and just functions. So here we have some TypeScript, and the first three lines are just declaring the types of our dependencies and our unit. So the top dependency A again is a function that takes a string, returns a number. The second dependency B is something that takes a number, returns a boolean. So that's again the case. The top case again is just counting the characters of a string to number. And the second one's comparing a number with the number 10, number to boolean. And then we have the unit type, which is the same as before. It's just something that takes a string, returns a boolean. Is this string longer than 10 characters long? And then we have a new type here, which is the fourth line, which is type unit creator. And the unit creator takes its two dependencies and returns the unit. And so that's the type definitions out of the way. And then the last three sort of lines of code are the actual implementations. So the first code, the create unit, is a function that takes dependency A, dependency B, and gives a unit. It's a unit creator. And all it does is compose those two functions together. So it calls dependency A first, and then sends the result to dependency B. And And the last two lines show how we can create the unit and run the unit. And you can see how concise it is there, create unit and passing in the two functions I need as its dependencies. The first function is the length of the string, and the second function is comparing a number with the number 10. And so this is entirely equivalent to the class-based system we saw earlier. Okay, so we've said a unit can depend on other units, but there's one really important caveat. And that's a unit can depend, for it to be a true dependency, I must be able to create an instance of that unit with something that looks like the dependency but isn't it. And when I say looks like, I mean it has the same public interface. So here we've got a big green unit of code that depends on the orange unit of code. Now, that is only a true dependency if I can create an instance of the green unit with something that has the same public interface of the orange one. Maybe it's string to string, takes a string, returns a string, but is different. So I can swap it out with different units. And the reason that this is so important is because I want to be able to extract a dependency for that one line of code, that small bit of code that needs to hit the network, that needs to interact with the outside world. And if that's then a real dependency, when I'm running my tests, I can swap it out. It's called stubbing. I can swap it out for something that looks like the real dependency that interacts with the network and interacts with the outside world, but actually doesn't. It's just something else. And that allows me to test every single other line of code, everything else in my program, without needing that network connectivity and without needing the infrastructure that's needed to test those small dependencies. Okay, so now I'm going to show you an example of extracting a dependency with side effects. So before, we're going to have a single unit of code. It's got some inputs, it's got some outputs, and there's a leaky arrow into the outside world, so I know it performs side effects, I know it interacts with the outside world. After the refactor, we're going to have, again, the same big unit with the same inputs and the same outputs. It's going to do the same thing. But that little bit of code that interacts with the outside world will have been extracted into a dependency. You can see the leaky arrows now in the dependency. And then I'll show you how easy it is once that's in place to just swap that out in the test for something else. So I'm going to use, this is a TypeScript functional unit. It's called create user. It's going to create a user for our web app. The input is the username and the output is the newly created user. It does a few things. It creates a date, creates a timestamp, and then it creates a new user. It creates a new user with a new ID. It then constructs some SQL to insert that user into the database, and then it actually inserts it into the database. And this is the code that needs the outside world. This is the bit that calls the database. It creates a database client, connects, queries, and releases. So this is the bit of code that we're going to extract into a dependency. But what about this? Like if I'm extracting some code to run some SQL, maybe I should also extract this line as well, the bit that constructs the SQL. And so we're going to compare both cases. A, just extracting the client code, and B, that and the SQL. So the first case that we're going to compare is this one, the client code, just the bare minimum. So the first line of this code is the type definition for our new dependency. It's called SQL executor. It takes some SQL, a string, and it returns nothing. It's void. And this is typical for a side effect unit. It's not always the truth. It's not always the case, sorry. But if a function returns void, it's returning nothing, so we know it's going to be performing some sort of side effects, otherwise there's no point having that function. The next block of code, the create unit, is the unit constructor, and this does everything as it did before. It creates a timestamp, it then creates an ID and creates a user, it then generates a SQL, but instead of running that SQL, it delegates it to its dependency, and it just runs its dependency. Now, the interesting thing is the 4 lines at the bottom of the program, which show you, well, first of all, lines 25 and 26, and that shows how we create instances of these units. So for the first one, for the production case on line 25, we create the unit with the proper code, the execute on Postgres code. That's going to go in and actually write to the database. But for our tests, we can just create a unit with something that does nothing. It just returns null. It does absolutely nothing. And so I can test all the other lines of code, but for the actual line where I'm supposed to be executing SQL, it's just going to do nothing. Now, you may want to inject a sort of in-memory equivalent to the real database, so you can then read and write and have a test that does a bit more testing. But for now, this shows the point. And the last 2 lines show that you can use both units exactly the same and just call them with the data they need to actually run the units. So this is the second example where we extract the code that writes to Postgres and the code that generates the SQL statement. It's very much the same as the last example. The main difference is that the public interface of our dependency has changed. So before we had SQL executor, which took a string, some SQL, and returned void. Now we have, it takes the whole user. And so its name's changed. It's now called a user persister instead of a SQL executor. But other than that, everything's pretty much the same, except that now my real code, the persistent Postgres function, also has the extra line in where it creates the SQL. And now the important thing to remember here is that everything in that persistent Postgres function will be stubbed out when we actually run the tests. So this line of code will no longer be tested. Whereas in the other case, it was tested because it was still in the old, it wasn't stubbed out. And so this leads us to our next sort of subcoding principle, and it's we should make these side effects as units as small as possible. So extract dependencies to contain side effects and make them as small as possible. This is a little bit up for debate. I think this is the way to go, but in doing so, you are affecting the public interface. So people might choose not to make them quite as small and have better public interfaces that are more reusable. You can still do that, but you're going to have more units. So you just need, I can't go into any more detail because of the time, but the point is we're showing the pictures and we're discussing the effects that we have. Okay, so the next question that arises, now that we've decided we're going to construct our code in units, we're going to design our code in units, the next obvious question is, how do we put these units together to create a complete program? However we do it, has to be consistent, it has to be the same, whether we're running functional TypeScript on a Lambda, or whether we're running object-oriented Golang or Java in a Docker image in ECS. So I'm going to propose, well, actually, the thing to notice, though, is that there's always an entry point function. So there's always a contract, a function you have to implement, and that's the thing that gets run. So if you're running a Java console app, there's going to be a main method that has to return void, I think, and take some string args. If you're running a Lambda, then you have a function you have to implement that takes a request object, and you need to return a response object. This entry point function already exists. You always have to run it. Now, what I suggest you do in that entry point function is you only ever do 2 things. First of all, you new up a single unit. You create a single instance of a unit, and this means that you have to also create all its dependencies, and then run it. And that's an example here for a Java main function. So this may be running on Docker in ECS, or it may be running on the command line. But all we do is instantiate that root unit and then execute the unit. So why must we do that? Well, I know that the code in the entry point function isn't going to be tested. I can't test it. Well, let me rephrase that. It's not going to be tested without network connectivity. I'm not going to be able to run it each time I edit a line of source code. Because I know in that unit, and knowing that entry point function, I'm going to have to new up my instances that talk to the outside world, and I'm going to have to run that code. So I know that I'm not going to be able to test that unit. So I want to do as little as possible in the entry point function because it's untestable. I've kind of got to create the unit though, and I've kind of got to run it because otherwise how else am I going to start my app? But anything else I don't want to do. And we're going to look at this little example here now in Java, and I'm going to show you these 3 lines. They're pretty innocuous. They're getting the environment variables, they're getting the Postgres connection details from environment variables so that we can connect to Postgres. But it's logic, and I know that logic isn't tested. And so I want to move that out the entry point function. And a starting point, I might put it in the constructor of one of my units. So here I've put it in the constructor of the Postgres unit. But actually, this isn't going to help because I know that everywhere in my code, I'm going to be stubbing out that Postgres unit. So I know that's not going to be running the tests. And so again, it's the same. The only place that code is going to be run is in the entry point function. And so again, I know that code isn't tested. So how I would fix this problem is I would create a new unit that is here at the bottom of the file called Postgres config provider that provides those variables at runtime when you run the unit. And now I can test that just like I test every other unit. And now all the code, I have as little code as possible, as little logic as possible in the entry point function. Now this is up for debate because now you've got issues with caching that you didn't have before. You might have issues with race conditions that you didn't have before. So you don't get it for 3. It's just this satisfies my need to test as much as possible without the network connectivity. And it leads to our last sort of sub coding principle that logic should be executed at runtime, not at creation time. So I want to run no unit when I'm creating, I want to run no logic. I want to have no logic when I'm creating the unit. I want all my logic to be when I'm running the unit. And so from that simple coding principle of as much code as possible should be testable without network connectivity, we have lots to talk about. We have the pictures to show, but I want to structure code in units, extract dependencies to contain side effects, and make those side effects dependencies as small as possible. Don't inject data. I haven't talked about that. That is, if you are taking data in the constructors, you have to ask the question, where has that data come from? Some logic's provided it, and so that means that it's happened at creation time. So it's just another way of saying no logic in unit creation code. And finally, applications should just create a single unit and run it in the entry point function. Okay, so we've got one more quick coding principle to go through. It's my favourite one, but I needed to get units out the way first, so it's short and easy. I have a single data object called data. It wraps around a string called value, and I have a single unit which takes a single dependency. And when I run this unit, line 21, all it does is it runs the dependency, and the dependency returns its output of this data. And we're going to print the value on that data 3 times. And the question is, what is the output of this system? Are those 3 lines going to be the same? And the answer is that we have absolutely no idea. It may be that every single one of those system out print lines has a different value. And that's because it may be that dependency starts a new thread that just constantly changes the value of the thing it returns. And so this isn't good code to reuse because, and we'll get to that in a second, but let's change that data class a little bit. And all we're going to do is on that second line, we're going to add the final to the value. So now it's immutable. I know that whatever that string is never going to change. And so now when the unit calls that dependency, I know that every one of those print lines is going to print the same thing, because I know the data that that dependency returned can't change. And the reason this is important is because we need to be able to consume these dependencies without having to know about their internals. So imagine I've got this green unit here with these two dependencies, a pink and an orange one. The pink dependency is also going to have its dependencies, and its dependencies are also going to have its dependencies. Now, if I'm writing that green unit, I want to code fast. I want to go, well, I don't want to have to go through all the code base to find the dependencies of the green unit and find the dependencies of the pink and then the green and the orange and their dependencies and their dependencies. I want to be able to just look at the one thing I'm consuming at its public interface and know how that's going to behave. And the only real way I can do that is if I know that the things that it consumes and the things that it returns are immutable. And so this is my favorite coding principle, that all units should have immutable outputs and immutable inputs. And so there it is. There's the coding principles that I always start with. It's not really about that, it's about being able to express these ideas with pictures and words, and not mattering which programming paradigm or which programming language we're using. So at that point, thanks for listening. I've uploaded some blogs at this address so you can read a bit deeper about these ideas. There's not a lot I can go through in sort of 35, 40 minutes. Sales Cycle Hiring, it's a great company to work for, good tech stack. You can tell it's a nice place to work because I still refer to it as we, even though I don't work there anymore. I have moved on. I am now focusing my efforts on Roland Street Software. At Roland Street Software, we can help you make the move to these serverless environments where you don't have to worry about managing servers. And the total mind-blowing thing about Roland Street Software is that we can generate your entire application, back-end, front-end, UI, data stores, cloud infrastructure immediately. And we have a bit of machine learning, a bit of in-house apps that we can generate, so you can have risk-free outsourcing, because you can have a poke about, review the code before you commit to pursuing that or not. Again, you can contact me through the Roland Street website. That's the shameless blogs out the way, and I will answer any questions that anyone has on any of this. Thank you very much for listening.